Hello, welcome. This is part of the series on the Libre-SOC processor. This is the load store computational unit, and it's going to be divided into two halves. First, we're going to cover load, and then in the second video we're going to cover store. The reason is because it's quite a lot to go over. It's a particularly complex diagram. The processor is based on an augmented version of the CDC-6600 from 1965, augmented very kindly with assistance, several months of help from Mitch Alsop, in particular to turn the dependency matrix system into a precise exception system, which is very unusual. Most people from reading the academic literature and from the patent believe that 6600 is incapable of being adapted to precise exceptions, and that the only option therefore is Thomas-Sula algorithm. And secondly, they believe that it is incapable of being adapted to multi-issue, where Mitch Alsop explained that by converting it to register the dependency matrices and what's known as the Q table to an unary form, where the patent is listed as a binary form, a binary index onto the thing. You switch that over to a unary encoded. You can do multi-issue very, very easily using transitive relationships. So this is the reason why we're using the basics on the 6600. Now, the computation units are basically to have signaling in pairs. We decided to go, rather than a single signal for in the traditional 6600 design, you have a single read and acknowledge, request and go read, dealing with all incoming ports, arbitration of all read ports, and likewise for write you have a single write arbitrating the one in the case of the original 6600, but this one has two because it's got to update, arbitrating the one write port. Consequently, you've got a bit of a mare there. So what we decided to do is to split it into two. Alright, so you have a go write 1 and go write 2. Now, because we're doing a power instruction set also has update mode, so that the effective address, which is computed here from either the immediate or operand 2, can also be stored. So you have a possibility of, I always get this wrong, 3 reads, one write, or 2 reads and 2 writes, depending on whether you're load or store. So this time what we'll do is we'll go over the load thing, and we'll use these peppercorns to tell us which latches. These are SR latches, which are much more efficient, by only being two NAND gates. And the way that it works is it does not need a reset system, and does not need just D flip-flops. We may end up using synchronous latches in because for simplicity of being able to verify them, whereas SR latches are notoriously difficult to verify using standard tools. So we've got the one latch which looks after the opcode, right? And when basically, if this is set, that's reset. So it's all set, reset, set, reset. All right, the circle on there mean not mean for reset. That this output is Q dashed and this one is Q. So when this is when it is set, any opcode coming in here will just be randomly floating and go through. However, when you clear it, reset it, whatever was on that register at the time will always be persistently outputted indefinitely until the latches reopen again. So you have the actual opcode. We have operand 1, operand 2, operand 3. We have an ALU latch, which takes care of protecting the output from the ALU and latching that. We have an address latch, which says that the address is valid and makes a request for it later. We have a store latch, a load latch, a write latch, because you want there's a different thing from acknowledging the load and latching the load result here, as different from the actual writing of that to the register when the register file is ready. We have an update, which up here takes care of storing the effective address, which was computed back here and stored in this one. And we have a reset latch, which is a reset condition, which brings us back to the start. So let's go first over the over load. Right, so we've got load. We've got two modes. In load, you've got load mode, you've got update, but you've also got an immediate mode. So we'll cover each of those separately. Right, so when you're in the reset condition, everything's gone. You've been happy. Then this indicates that latch is set, has been set. So let's assume that go die has been called, which clears the whole board, pulls everything back. All right. So that one will be set. Let's track it down. This one will be set. ALU will be set. Load latch will be set. And everything else is cleared. Okay. So the first thing that will happen is that issue will be pulled. The immediate opcode will be put on the bus simultaneously with issue being pulled, and that will result in the immediate being set to valid, and this one will go to this thing. But at the same time, you come out of capturing the opcode mode, and you now want the operands 1, 2, and 3, and load is still in set. Remember, it's a latch, so it will still be in set mode. The write will be set, and that's it. Okay, so this is anomalous, but if you notice, there's some logic here which disables it, so it will not request a write because the load result is not yet ready. Right? Okay, notice that not gate there. So this latch is on, which switches off this AND gate, which disables request for a write. The one thing about these, so there's no special logic thing. Basically, these request signals, request read 2 and read 3, and the request write and require thing, those take care of the register file requests. There's no special command. It's not a thing. It's built in to the logic here. It's incredibly simple, a very amazingly elegant design. So what happens is that the request goes out, and you have multiple signals in different ports. You have multiple of these things. So you have a load store combination of 1, 2, 3, and 4, which will give you the ability to queue 4 loads or stores simultaneously. And you have a priority picker on the register port 1, 2, or 3, read 1, 2, or 3, and a priority picker on, well, maybe you have one write port, maybe you have 2, but if you only have the 1, then only one of these can be set, not just for this read-write request and this write request, but for all load store computation rules. So likewise for this request 1, read request 1, only one of them can be enabled for any of the computation units, not just the load store ones. But for any computational unit, a priority picker will select you one and only one of these to be enabled per register file port. and you will get a response saying go read, and on that signal the operand will come in here and this latch will go. So let's assume that you can see here busy, this request read is only set if our computation unit is in the busy mode, which was the negation of this op thing here. So the fact that that is being reset, Q dashed goes true, therefore it indicates busy. So that busy signal goes right the way down to every single one of these orange request gates. So let's say operand 1, the request read here, operand 1, go read comes in, that will reset that and it will switch this on, and now operand 1 is latched in, permanently locked into this register. By the way, if you prefer English words, I've got the words version of this here. I'll take some photographs of these and put them online and put them into the URL of the comments of the YouTube video. So now let's do immediate mode. When immediate mode on the opcode, we need to calculate the effective address here, and there's two different modes. One is that you have the index version, which is that operand 1 and operand 2 are added as inputs to the ALU for to calculate the effective address, or operand 1 and the immediate is brought in. So let's do immediate mode first. So immediate immediate OK is true, which this is a mux, which brings in the immediate muxing or the output of that. That's an and that's an and not. It brings in that immediate value into here, and consequently you get we're going to add the operand 1 with an immediate. Right, now notice that immediate OK also goes into the orange AND gate on a NOT. So when immediate is not set, read request 2 will never be set. So you will not see a second read request on the second register file read port, which is exactly what you want. Also, the request read signal comes down into this multi-input combiner, which says when this only goes true to tell the ALU it's valid when we're busy and request read is not set, and when request read 1 is not set. Okay, so both of those have to be satisfied. Now, given that it's immediate, this is off. All right, so this can never be true. That this is false. Therefore, that is true. That was true because we've had the operand latched in as well. The thing, so that is false. So when converted to thing, so that's condition is satisfied. Therefore, this ALU signal, ALU value gets triggered, and it is that only happens when the both inputs here are also valid. Now, what we've done is we're going to do this on a single clock cycle. So there'll be a single clock of delay, after which the ALU OK will go valid. All right. So that covers covers the load in immediate case. Right. So let's now do the load with indexed. So again, immediate OK is false, therefore that AND gate which ends in and ORs in the immediate is all zeros ORing in from there. However, because the immediate is false, this one is true, so op2 is ANDed in there and then ORed into the input from the mux. All right, but it's floating, it's random garbage coming in here at the moment because we haven't issued the read signal. Now, because that immediate OK is false, this is true. Op2 is latched high, Q is high, therefore, and busy is high, therefore request read is true. Therefore, at some point in the future, the priority picker will pick this particular line from the multiple lines coming in for this register port number 2 from multiple computation units, and it will assert a go read, and at that point Q will go low on here, and that will latch, result in whatever input was on op2 at the time, which happens to be the output from the read port 2 of the register file. That will latch that in. Then this AND gate will go low, therefore that will go high, that input high, that will go high as well, and correspondingly the ALU valid signal will go high. Ta-da! Alright, so through the mux. So that 1 clock later, the ALU OK signal will go high, and we will have our effective address. Now, let's ignore this one for a moment. That's operand 3. All right. So ALU goes high here, which we can see the signal tracking through to this reset on this one, and that goes low, so the ALU.Q goes low, and the effective address latch becomes a valid input because this line becomes false. Right? Note, however, that ALU OK enables the address one, and it enables the update latch down here. So that ALU OK goes to ALU and address, cancelling that one, enabling that one, and then enabling the update latch. Now, alright, so now let's pay attention to this. Whoops. Now let's pay attention to the update thing, because we the power PC power instruction set has an update mode where the effective address can be written to a register. This hint that controls it. Okay, so let's assume update is true. That goes into this AND gate here. Update mode is true, and the various other signals include where is it? Shadowing. Now, shadow mode is for precise exceptions. Basically, when there are any possibility of damage being made by write that's irreversible, you must pull this shadow line, shadow N, low, and that will disable anything which can cause damage, irreversible damage. Right? So you can calculate it, but you can't write it. Okay? Right? You can also do operand forwarding from things, but you can't write it to the register file. Okay, so the output from these write ports can be can go on a forwarding bus back into reads, and one of these will allow it to do that. Be allowed access to this, to the requests are allowed access to the forwarding bus. However, actual writing to the register file is not permitted. So you can propagate through the forwarding bus. You can propagate throughout multiple computational units results that have not been committed yet. And finally, when there is no possibility of damage, the shadow goes back higher. Shadow N, shadow inverted, goes high, allowing write permission thing. And one of the reasons why you need that in this particular load store computation unit is because of address exceptions. So if there is a possibility the address is out of bounds, or there's a level 2 cache violation, or a page table walk exception, anything like that, you do not allow the to proceed until you absolutely know. You keep this low until you absolutely know that there is no possibility of damage from an exception or anything else. And this is also pulled for branch prediction and everything, precise exceptions, branch prediction, branch speculation, sorry, predication and load store exceptions all go through this shadow mechanism. And that's the thing that Mitch also very kindly explained to us. So coming back to here, okay, all right. So update is true. And let's say that shadow n is also on. So all the conditions are satisfied for this gate here, for this AND gate, to be request a write. Ta-da! So that request goes out, and it's actually this here which will be written out. Okay. So now, if that was not set, if update was not set, then update doesn't get this AND gate doesn't think, and no request for that register file port write port will be made. It's real simple. So let's assume that it's staying in that mode. Right. But notice that that's independent, completely independent from the actual load and store logic. Right? It comes from the effective address. It's controlling effective address, and that's basically the advantage of this multi-signal approach here. You have instead of one signal per write port, you have one signal for each write port, one signaling pair for each port. So we're doing load, right? Now, in this, we're not doing a load request. We're assuming that if you're in load mode, I must bring those two signals into here as well. Load and store. Go dot dot dot. Okay, right. So that is load and that is store. Okay, right. Indicating which mode this the memory port request is being done. This takes care of MMU, TLB, level 1 cache, level 2 cache, etc., etc. We don't care as far as this is concerned. Right. The only thing we care about is did the address computation succeed? Was there an exception? But when you do the load mode, at some point in the future, it may be one cycle, it may be n cycles, depending whether it's a virtual memory lookup or not, you will get a load OK signal, right? And at that point, this latch will go off, and the load data will be latched in on the same cycle. Right? And at that point, the load OK signal can go low. It doesn't matter. So we have a conventional system here. Now, notice this, the NOT gate going into here. So go back a bit, right? When that was true, this was false, and you did not request a write for that load register. That's very deliberate, right? When the load OK signal comes from the memory system, latching in that, switching in this off, that will go high, and the conditions for the request write to the register file, request write, will go high, and those conditions are busy, yes, write is being requested, yes, load data has come out and is latched in, yes, shadow n, yes, what are the other ones? Oh yes, it's a load, yes, so that's 1, 2, 3, 4, 5, 6. All right, so there's 6 separate conditions which must be satisfied for this to be for that to be on. So it's on, it's done, bink, and this gets the opportunity to go out onto the request write one not broadcast bus, for which covers all computation units, but you get the general idea. All right. So let's check down here. This is a critical part of the logic. It says when everything has been done condition, and it basically has to be the reset latch has to be all right. The thing well, nuts. Address OK. How annoying! I'm terribly sorry. I missed one. Address OK went high, which enabled that. Back when the effective address was computed here, and you had a go address come in here at some cycles, whatever it is, when all computations of the address, level 1 cache reservations, level 2 lookups, etc. The address says it's okay, and bink, these two puppies go enabled. The store latch is enabled, and the reset condition latch is enabled. So that this input will be high into our write reset, our reset thing, which goes back, and we're all done. So busy is true. The update signal is false in the case of update being false. That's an ANDed into here, so that cancels that, therefore that will be true. However, if we had an update condition, then think that would be, update would be true there, so this will be enabled, therefore reset condition would not be permitted to a thing until update a go write 2 came in, which allowed you to put this data onto the write bus to register port 2, write port 2. At that point, that will go false. This AND gate would all go false. Therefore, that write condition would go true as well. Right? We have another one. All right, coming back to, yep, we've done our write to the. The go write is for load. Yes, so we've done our load, so we've done the store. Therefore, the request is now low. Therefore, the inversion of that onto the write reset is now high. So that one's high, and we have our shadow n as well on here. So only when that shadow n is high will this be allowed, but also note there's this store one here as well. Okay, so we're not doing a store. However, if you look, there's this line here which goes back to store, and of course we're not doing a store, so that is off. Therefore, that AND gate is off. Therefore, we're not doing a request store, which means that the inverse of that means that this is true. Ta-da! Now, we also had to bring in a condition of whether we were requesting a store or whether there was a load, because otherwise this could blip for a single cycle during this thing. So when you are not in load mode, what was it? Load, that goes high, therefore that goes low, therefore it does not reset. That was it. So when this was back here, when load was had not yet been requested, not been acknowledged as okay, this would be high, therefore that AND gate would be inverted, therefore that would be off. And yeah, that's okay. All right. When that goes on, then it's okay. All right, good. All right. So that basically covers the whole thing, this whole process for load. It's very, very detailed, this one, and compared to the 6600 load store computation unit, it's a lot more complex. The thing is, half of the logic involved, and it's because in the original 6600 and most RISC systems, you just don't have this 3 operand thing. You have the store data. You have only one address. You don't have the index mode. You only have the immediate version, and you only have one register to write out. You certainly don't have the indexing, but the opportunities for optimizing the assembly code are so much greater. We're just having this discussion on comp.arch about this. Many thanks to Bruce Holt and to Mitch Alsop and Terj for helping to review this and contribute to the discussion. Thank you very much.